Hello there, Mr. Sutton here, bringing you these BC Calculus 518 Extra Practice number 4 solutions on improper integrals. For this problem, we're trying to take the integral from 1 to infinity of this expression here. Now, since we have an infinity in the limits of integration, this is an improper integral. That means we need to rewrite this using a limit. So I'm going to call this limit as b approaches infinity of the integral from 1 to b of all this stuff. And my next step, I'm actually going to rewrite this as 6 times all this stuff to the negative 3/2 power, just to make it a little bit easier to take the antiderivative. And now what is that antiderivative? Well, using my reverse power rule, I can bump this up to a negative 1/2 for the exponent. Dividing by negative 1/2, also known as multiplying by negative 2, we've got a negative 12, x plus 3, all raised to the negative 1/2 power. And we still have the limit as b approaches infinity. And we're still going from 1 to b. All right, so let me keep this negative 12 kind of pulled out of there. And inside now, plugging in 1 and b, I'm going to have, this is actually going to be 1 over the square root of b plus 3. And then we're going to have minus 1 over the square root of 1 plus 3. So as b approaches infinity, this first term here is going to go to 0 because you have an infinitely large denominator versus a constant numerator, so it's a bottom-heavy function. This other term, this is just going to be negative 1/2 inside here. So then we have negative 12 times negative 1/2, giving us positive 6, which is going to be choice C. On this problem, we're trying to take the integral from 0 to 1 of 1 over 1 minus x. Problem here is that we have an issue at x equals 1, a discontinuity there, because you're dividing by 0 at that point. So because this is an issue, we have an improper integral, and we're going to have to rewrite this with a limit. So I'll call this the limit as b approaches 1 from the left side, so we're approaching from inside this interval here, of the integral from 0 to b of 1 over 1 minus x. So basically I just rewrote it with us approaching the problem spot instead of us actually being at the problem spot. So now antiderivative of this, we're going to have ln of absolute value of 1 minus x, but I'm going to have to divide by a negative 1 because of this negative x, negative derivative there. So we've got this going on. Still have the limit as b approaches 1 from the left, still going from 0 to b. Plugging stuff in now, we've got negative ln of 1 minus b, and we're going to have minus minus, so plus ln, absolute value of 1 minus 0. Well, this ln of 1 minus 0, that's just going to be 0, so that's fine. But over here, as b approaches 1, this ln has an input that's essentially approaching 0, and ln is undefined at 0. So this does not exist as a limit, which means our integral diverges, and we're going to have to pick choice D. On this problem, I'm trying to take the integral from 4 to infinity of 1 over x cubed. So this infinity is a bit of an issue. I'm going to get around that by expressing this as the limit as b approaches infinity of the integral from 4 to b of, and instead of writing 1 over x cubed, I'll write x to the negative third, just to make that a little bit easier to take the antiderivative of. So I've expressed my improper integral in a less improper fashion. Now that I've got this infinite limit going on, let me take my antiderivative and sort this out. So using the reverse power rule, this bumps up to a negative 2. Dividing by that, we have negative 1/2 x to the negative 2. Still have my limit as b approaches infinity, still going from 4 to b. And I'm going to yank this negative 1/2 out of here. Inside, I'm going to have 1 over b squared minus 1 over 4 squared. As b goes to infinity, this first term here is bottom heavy, and so it goes to 0. So we're just essentially left with negative 1/2, and in here we've got 0 minus 1 over 16. So negative 1/16 then. Multiplying these out to get an answer choice, we end up with 1 over 32. So that's going to be choice C. On this problem, we're asked about the integral from 0 to pi of sine of x over 1 plus cosine of x, and we're told that the antiderivative of this thing is negative ln of 1 plus cosine of x, which was awfully nice of them to just give us that. So that's already half the battle. But now, why are they giving us this weird integral? Well, the issue with this one is when you plug in pi for cosine, that comes out to -1. 1 minus 1 is going to give you 0 in the denominator, so we have a discontinuity at pi, which means this is an improper integral, and we're going to have to actually express this using a limit. So I'm going to call this the limit as b approaches pi from the left of integral from 0 to b of this stuff. And I'm doing this because this is an improper integral, so that's how we deal with it. Express it as a limit. So now I have to take the antiderivative. Fortunately, they already gave it to me. So this is going to be limit as b approaches pi from the left of negative ln of 1 plus cosine of x evaluated from 0 to b. All this stuff. At this point, I just have to plug in 0 and b and see what happens. So if I do that, I've got all this stuff with b plugged in minus all this stuff with 0 plugged in. So I'm going to actually be doing minus minus, so plus ln of 1 plus cosine of 0. And as cosine approaches, as b approaches pi, this term in here, you're basically taking the ln of 0, or something very close to it. So ln then is going to be going to one infinity or another. It's going to be undefined. So this is the issue here, is that this limit does not exist. So now looking through the answer choices. Choice A, the integral equals 2 over pi. Nope, limit didn't even exist, so the integral doesn't really equal anything. Doesn't equal 2 over pi, it doesn't equal ln of 2. Now we get down to choice C. The integral diverges because the limit of this stuff does not exist. That's not necessarily true. So the big issue here was that the limit of this expression here did not exist. The limit of the antiderivative did not exist. The original not existing for the limit, that doesn't actually cause the interval to diverge. It's all about the antiderivative and that interaction with this limit. So choice D is a better choice. So that's why this integral diverges, because this antiderivative did not exist. For this free response problem, we're using the function family 1 over x squared minus 2x plus k for some constant k. First part of this problem, they want us to find a positive value of k so that the slope of the tangent line for this thing is going to be 6 if x equals 0. All right, so let's go ahead, and if we're talking about tangent line slopes, we should probably take the derivative of f just to see what that looks like. But before I do that, I'm going to rewrite this just so I don't have to use the quotient rule. I'm going to write this as x squared minus 2x plus k, all raised to the -1 power. And now if I take my derivative of this, this is going to be a chain rule. I'm going to have negative all of this stuff to the -2 times the derivative of x squared minus 2x plus k. So that's going to be parentheses 2x minus 2. And now they're telling me that when I plug in 0 to this derivative, I should end up with a value of 6. So I'm going to rewrite this as a fraction here. This is going to be, my 2x minus 2 is going to be in the numerator, and this is going to be 2 times 0 minus 2 up there. I've got a negative fraction overall, and in the denominator, I've got 0 squared minus 2 times 0 plus k, all of that squared. And they said I should get 6 when I plug 0 into everything, so let me say equals 6. Time to simplify a little bit. So in the numerator, we just have a -2, which I'm going to negate because of this negative out in front to make it a +2. Down below, the only thing left is a k, and that's being squared. So when the dust settles, we have +2 over k squared equals 6. All right, well, I'm just going to cross multiply, basically switch the k squared and the 6. So I can write k squared equals 2 over 6, or 1 over 3 if I reduce that. And then if I take the square root of both sides, I'm going to get k equals the square root of 1/3. Now, I would write plus or minus 1/3, but they told me right in the beginning of this part that k is positive. So I don't have to write the negative root. I just keep the positive, and I call it a day on part A. For this next part, they're saying if k equals -8, they want the integral from 0 to 1 of this function. So I'm essentially looking for integral from 0 to 1 of 1 over x squared minus 2x minus 8. Now, to take this antiderivative, I mean, there isn't really much you can do to simplify this. Really, our only possible option here is to try to factor it and use integration by partial fractions. So if I do factor this, two things that multiply to -8 and add up to -2, that's going to be x plus 2 and x minus 4. So I'll split it up like that. And then I'm just going to do my little partial fraction dance. I'm going to write that this equals a over x plus 2 plus b over x minus 4. And I will now go out and find a magical a and b value that actually make this thing true. So if I can split this up in this fashion, then I can just do the ln antiderivative on each of these individual terms. But got to get a and b first. So to find that, I'm going to multiply everything by x plus 2 and x minus 4. That gets rid of my denominator on the left side, giving me just 1. On the right side, for this first fraction, the x plus 2's are going to cancel, so I've got a times the x minus 4 that's left over. And over here on the second fraction, on the right side, the x minus 4's are gone, so now I have b times the x plus 2 that's left over from that. And to solve for a and b, now I'm just going to pick a convenient value of x that gets rid of one letter or the other. So if I want to solve for a, let me pick the x value -2, because -2 plus 2 would zero out this b term. So if x equals -2, I can write 1 equals, and now this is going to be -6a left over. So that means a is going to be -1 over 6. And now to find b, I have to get rid of the a term. So if I let x equal 4, I can write 1 equals, and now this a term's gone because it got zeroed out. So I just have b times 6, or 6b. So that means b is going to have a value of 1 over 6. All right, going back to my integral, I'm going to split this up now. I can write, instead of a, I can write a -1 over 6 over x plus 2. And actually, I'll do this b term first here. That's a good idea, so that I'm not putting my negative first. So let me do 1 over 6 over x minus 4, because that's what my b value was, 1 over 6. And now let me do my a term next, since that's going to be negative. So now I have -1 over 6 over x plus 2. Don't forget the dx there. This is a free response, so proper notation is important. Now taking each of these antiderivatives, I'm going to end up with, well, actually I can take a 1/6 out of this whole integral, and then inside I've got 1 over x minus 4, whose antiderivative is just ln of absolute value of x minus 4. And then I've got minus, this is now, since I took out a 1 over 6 from everything, this is just 1 over x plus 2, whose antiderivative is ln absolute value of x plus 2, and I'm subtracting that. Still evaluating from 0 to 1. Before I do that, though, let me just merge these together into one big log. Since I'm subtracting these, I can divide the stuff inside. So this is just ln of x minus 4 over x plus 2. Still leave that absolute value around just to be on the safe side. And now I've got ln of, I got a 1/6 still, and now I've got ln of 1 minus 4 over 1 plus 2. Oops, there we go. Minus, now we've got ln of absolute value of 0 minus 4 over 0 plus 2. So this is ln of, let's see, -3 over 3. That's -1, which is +1 with the absolute value. Ln of +1 is just 0. So that whole first term is gone. For this one, I've got -4 over 2, so that's -2. But the absolute value makes this the ln of +2. So when the dust settles, I have 1 over 6, and then here I have a negative ln of 2 to go with my 0 there. So I could leave it like this. Honestly, I could have stopped at this point right here, or I can multiply it through to get -1 over 6 ln of 2. For this one, I'm going to let k equal 1 and then find the value of 0 to 2 integral of f of x, or show that it diverges. So this is going to now be 1 over x squared minus 2x plus 1. And on this one, I can actually factor this as well. So this is going to be, let's see here, two things that multiply to 1 and add up to -2. How about x minus 1 and x minus 1, or x minus 1 squared? Now this is something I could actually take the antiderivative of. Before I do that, though, I have a bit of an issue. The integral is going from 0 to 2, but at 1, we have 1 minus 1 giving us 0 down here, so we have a discontinuity at x equals 1, making this an improper integral. And this is pretty much the worst kind of improper integral because the problem is like in the middle of the integral. It's not one of the endpoints. There's not an infinity I need to worry about. It's in the middle. So I'm going to have to split this up into two different integrals. I'm going to have limits in both of them. So for my first integral, which is basically going to go from 0 to 1, I'm going to have the limit as, we'll say b approaches 1, of the integral from 0 to b of x minus 1. I'm going to rewrite this as x minus 1 to the negative 2 power dx. So basically, I'm approaching that problem spot of 1 from the left side. And I'm not going to quite get to 1. I'm getting as close as I possibly can. That's what this limit here is doing for me. Now, I have to take that limit and add to that the value of the limit as, we'll call it as a approaches 1 from the right side. A approaches 1 from the right of the integral from a to 2. So this handles all the stuff between 1 and 2 now. And we're getting super close to 1 from the right side, but not quite getting there. Same stuff inside, though. So now taking my antiderivatives, I can just use the reverse power rule on this. This bumps up to an exponent of negative 1. Dividing by that, I've got negative x minus 1 raised to the negative 1. And I'm evaluating that from 0 to b using this limit as b approaches 1 from the left. And I'm also evaluating pretty much that same stuff from a to 2 as a approaches 1 from the right. All right, so plugging some things in. I've got limit as b approaches 1 from the left of, this is going to be negative 1 over b minus 1 plus 1 over 0 minus 1. And over here, this is limit as a approaches 1 from the right of negative 1 over 2 minus 1, and then plus 1 over a minus 1. So what happens if b actually approaches 1? Well, I end up dividing by 0 here. And I also, if a approaches 1, I end up dividing by 0 here. But really, just one of these divisions by zeros is enough to make me dead in the water here. One bad apple spoils the bunch when it comes to integrals. So this whole limit here, because of that division by 0, just does not exist. Which means that this integral up here they wanted me to take diverges, and I've just shown that, and I don't have to do anything else. For this free response problem, we're given the function f of x equals 4 over x squared, and our first task is to approximate the integral from 1 to 12 of f of x using a left Riemann sum with these subintervals. All right, so I'm going to write that this is approximately equal to the following. And I have to write approximately equals, or I already get dinged a point for not being mathematically accurate. All right, so left Riemann sum. We basically have 3 rectangle areas of a base times height sort of format. The base is just going to be the distance between the x values. The height is going to be what I get when I plug one of these x values into the function itself. But which x value? Well, since this is a left Riemann sum, I always have to choose the left endpoint of each of these intervals. So my first rectangle area, I'm going to have a base of 3, because 4 minus 1 is 3, times 4 over 1 squared, because I'm plugging my left endpoint into this function here. For the next one, I have a base of 4 times a height of 1 or 4 over 4 squared. And then finally, I have a base of 4 again from 8 to 12 times a height of 1 over 4 over 8 squared. I keep wanting to say 1 over. It's 4 over 8 squared. And whatever all this adds up to is going to be our answer. Now, you could actually just leave it this way, but I know, what fun would that be? So let's simplify it just because. So basically, we have 3 times 4, which is 12. This next one of these 4s is going to cancel with this 4. Actually, another 4 is going to cancel with this 4. This is all just 1 for that second one. So I'm already having fun here. And then we've got, let's see, basically 16 over 64, which is 1 over 4. So this is 13 plus a fourth, which is going to be 52 fourths plus 1/4, which is 53 fourths if you really wanted to break it down to one fraction. For this part of the problem, they want us to find the actual value of the integral from 1 to 12 of f of x. So to do that, we're just going to use the antiderivative in the fundamental theorem of calculus. Let me start by actually rewriting this, though. I can write this as 4x to the negative 2, just to make it a little easier to use the reverse power rule. Now this exponent bumps up to a negative 1. Dividing by that, we have negative 4x to the negative 1, evaluated from 1 to 12. And I can pull a negative 4 out of this, And inside I'm going to have, this is a 1 over x situation, so 1 over 12 minus 1 over 1. It's all constants, so I can leave it like this, or I can keep going. 1/12 minus basically 12/12 is negative 11/12. And let's see, the negatives are going to cancel. This really reduces to 1 over 3, so we basically have 11 over 3 when all is said and done. For this next part of the problem, they want us to find the integral from 1 to infinity of this function. Since this is an improper integral, I need to rewrite it with a limit. So I'll do limit as b approaches infinity of the integral from 1 to b of 4 over x squared, or 4x to the negative 2. And the good news is I already took this antiderivative. We said that from part b it was negative 4x to the negative 1. So now I'm just evaluating this same expression from 1 to b as b approaches infinity. So still yanking out that negative 4, because why not? And now we have 1 over b minus 1 over 1. Well, as b approaches infinity, this 1 over b term just goes to 0. So this is really negative 4 times 0 minus 1, which just comes out to 4, because negative 4 times negative 4 is 4. Done. For this problem, they want us to find the value of integral from 1 to 12 of f of x times ln of x. So this situation, I can't really simplify these things. I mean, I know what f of x is. It's this stuff here, but I can't do anything with that. So when there's nothing else to do with a product, we go with integration by parts. So here's my general formula. If I start with something in the form integral from a to b of u dv, and one of these things is u and the other thing is dv, we're going to have to pick in a minute. I can turn that into uv evaluated from a to b minus integral of a to b v du. So let's pick out u and v. Now, in general, I go with the acronym LATE, L-A-T-E. That's my order of preference for picking the u value. Logarithmic is the L. That always comes before algebraic, which was this 4x to the negative 2. And this is just really based on the idea that you want a u value that's easy to take the derivative of, and an integral, a dv value that's easy to take the antiderivative of. 4x to the negative 2 and ln of x, they're both pretty easy to differentiate, but integrating, it's very difficult to integrate ln of x. So if I have to pick one for integrating, I'm going to pick the 4x to the negative 2 for the simple fact that I can do it. So now let me set u equal to ln of x, and then the dv from this thing is going to be the 4x to the negative 2 dx, f of x dx. Derivative of u is going to be 1 over x dx, and I can write that as x to the negative 1. Antiderivative of this expression, well, we've done this like 3 problems in a row now. This is going to be a negative 4x to the negative 1. And now multiplying straight across here to get uv, this is going to be negative 4x to the negative 1 ln of x, and that's in an evaluation box from 1 to 12. And then now I get the integral part, the v du, by going this way here, v times du. So that's a minus minus, so that's actually going to be plus the integral from 1 to 12, 4x to the negative 1 times x to the negative 1 dx. I can actually make this 4x to the negative 2 if I combine those. And now let me go ahead and actually this is to be a dx in there. Ha! There we go. Much better. So now I've got this stuff that was already in my 1 to 12 box. I'm going to keep it in there. Also getting thrown into the 1 to 12 box is the antiderivative of this stuff, which if I bump that up to a negative 1 and divide is going to be negative 4x to the negative 1, same as this thing. Still being evaluated from 1 to 12. I'm about to plug in 1 and 12, but this is kind of a mess the way it is. So to try to make my life a little easier, I'm actually going to factor a negative 4 out of all of this stuff. That leaves me with x to the negative 1 ln of x plus x to the negative 1. And now these x to the negative 1s are really 1 over x's. So I've got a common denominator of x, essentially. I can rewrite the stuff inside then as ln of x plus 1, all of that over x. So that might be a little bit easier to plug stuff into. So now I've got all this stuff with 12 plugged in, minus all this stuff with 1 plugged in. This is going to be, let's see here, ln of 12 plus 1. Can't do anything with that, actually. This stuff over here, though, ln of 1 is 0. So this is just 1 over 1, or just 1. And if I really wanted to, I can combine these into a single fraction. This is really minus 12 over 12. So this would then be ln of 12 minus 11 all over 12. And then finally, if we reduce it with the negative 4, we get this expression here. That's a 1 over a 3. And we can call it a day. We really could have called it a day all the way back here, but I was having so much fun. So there we are.